Good morning. This is the first lesson in our second unit for term 3, and it's simplifying nth roots. So if you've never seen that expression before, the NTH, it's where you don't necessarily have a specific number. So you could have like the second or the third or the fourth or the fifth. And then if we want to generalize that, we just say the nth. So simplifying the nth root. And as I usually like to do when I'm trying to introduce something new is I want to tie it back into something you already know because the foundation has already been laid for you to understand what nth roots are. So we're going to start by looking at a square root. So we're going to start with a review of what we know. And typically we'll point out some important things about what you already know that maybe you haven't thought about. So for example, we have square roots. And we've talked a little bit about square roots earlier this year when we did imaginary numbers. The symbol for a square root is this here. It looks like a kind of a check mark with a long top on it. Please do not make your square roots and your division symbols look the same. They are not the same. This is actually what we call an operator in math. So an operator. And an operator is something that carries out an operation. It does something. Other operators would be the plus sign, the minus sign, times sign, division symbols, all of that. They all indicate what you're supposed to do to a number. And this symbol also indicates what you're supposed to do to the number. Namely, you are going to undo squaring. So the square root symbol undoes squaring. So we have, say, a 5 and we square it and we get 25. Then if I wanted to undo that, I would use the square root and it would bring me back to the 5. When you take the square root symbol goes away. Just like when you do the squaring, you no longer have the little squared symbol there. It's a symbol that tells you what to do. Now in the square root symbol, because it undoes squaring, there is an implied 2 as what's called the index. Okay, so this number right here, little sound effect there, is called the index. And if you don't see a number as your index, then you assume it is a 2. Not a 1, not a 0. I know in math, a lot of times when we don't see a number, we assume a 1 or a 2. Like if you don't see an exponent, you assume the exponent is 1. But with this, if you don't see an index, you assume the index is a 2. Now, a couple things about the index. The index has to be smaller than the size of the numbers you're using, and it needs to hover either right above the hook or would actually wedge inside of it. Okay, so it needs to be in that particular location, not this. Okay, it cannot be outside. This means 2 times the square root. It does not mean like just the square root or indicating the index. So I'm going to take the black and just write through it like that. Okay. So when you're writing your index, you have to make sure that it is smaller and that it's actually in the hook there. And so here's the deal with the square root. If you have, there's a reason I'm going to do this. If you have a 25 and you factor that into 5 times 5, then you can actually see the squaring and you can see that group of 2 and you know the square root of 25 is 5. So I know what I did there seems very weird notationally, but hang with me. There is going to be like a reason why I do that. So let's extend this. So we know that there's more that we can do than just squaring. For example, if I have 4 times 4 times 4, that would be raising to the 3rd power or cubing. And that just goes back to our definition of exponents. Well, there's a root or radical that undoes cubing, and that is called a cube root. And for a cube root, the index would be a 3. So this undoes cubing, and the index is 3. And so if you were to do the cube I'm kind of running out of space there. So if you were to do the cube root of 4 cubed, that would be 4. So it undoes it. You can kind of think of it as the cubing and the cube rooting undo each other, just like adding and subtracting undo each other, or multiplying and dividing undo each other. And just for the weird little notational thing, okay, that comes back to this, like 4 times 4 times 4. You see that group of 3, that means you're cubing, and so forth. So the index, that little number that's wedged into the crook of the radical, the index indicates what the radical, or the root, whichever word you'd like to use there, that's the name for that symbol, the radical or root undoes. So I'm going to give you like a bunch of examples so we can work through this. So for example, a square root undoes squaring. And remember, the assumed index is a 2. A cube root undoes cubing. A fourth root undoes fourthing. I don't know why I switched over to a 7 there. And so forth. Okay, etc. So when we talk about an nth root, it just means this can keep going up. So you can have a 5th root or a 6th root, and we run out of like words. Like I don't think fourthing is a word, or fifthing, but you guys get what we mean, like raising to the 4th power, raising to the 5th power. So when we are asked to simplify a radical, and we did go over this when we did complex numbers, it means get the smallest expression under the radical possible. So I'm actually going to write that out. And this is just what I said out loud there. To simplify means get the smallest expression possible under the radical. Again, that vocabulary, I know it's dry, but it's essential to understanding what the directions are asking you to do. If the directions say simplify these radicals and you don't understand what you're driving at, then you won't be able to carry it out. So that's where we're going. And when we were doing our square root, so this goes back to the complex numbers. If you have a square root, the way that we did it was we looked for the perfect square factor, and then we split up the radicals, and then we took the square root of whatever we could take the square root of, in this case, the 9. And I actually think that problem was on your quiz. But how does that work? How does this principle work when you have something like a cube root or a 4th root or a 5th root? What you're looking for are like perfect cubes or perfect fourths or perfect fifths. And the problem is that we don't actually know those numbers. We know perfect squares because somebody at some point made us memorize, sorry, that's stuck. I got a notification on my iPad and it made my marker stuck here. There we go. Okay, somebody made us memorize our times tables, and so we actually know those numbers. And we might do okay with the perfect cubes when we were factoring sum and difference of cubes. We learned some of them like 8 and 27 and 64 we know are perfect cubes. But virtually none of us know perfect fourths or fifths, except for very, very small numbers. So what I'm going to give you is a strategy for simplifying any kind of radical ever, and it's pretty foolproof, and it actually is going to work for square roots also in the event that you actually don't like square roots. The strategy only takes 3 lines from beginning to end. Maybe we might do like 4 just to be really clear on the explanation. The problem is that they will get long this way. So they're going to kind of stretch across your page. It's not difficult at all. It's just long. So here's the strategy. How are we going to attack these problems? First step is we're going to get the prime factorization. So prime factorization. And most of you don't have trouble with that. It's very, very easy with the variables. With the numbers, sometimes you'll want to grab a calculator and you just have to do some division out on your calculator in some scratch work. But pretty much prime factorization is you're going to break the expression up so that you can't break it down any further. I'll show you what that means. And then you're going to find groups of the size that matches the index. And I want that step to make sense to you. I'm not the magic math teacher, okay? So if you have, say, the fourth root, you're going to look for a group of 4. Why are you going to look for a group of 4? Because fourth rooting undoes fourth thing, or raising to the fourth power. That's why you're going to do that. Now, if you take the fourth root of that big group, you're going to get just the 7, because that's what fourth rooting does. It undoes the fourth thing. And so what's going to happen is you're going to have a 7 with no more radical over it. And as you get these groups that match the index, you're going to take the radical, the root, whatever it is, cube root, square root, fourth root, seventh root. Oh, heaven help us if there's a seventh root. We don't know. But whatever it is, and then you're going to write that outside the radical, and then you're going to have some stuff left over. So I have 3 examples to work through, so you get an idea of what this looks like, and hopefully you'll think it's easy. That's the plan. So we have here a cube root of 54 x to the third y to the fifth. And you can look at that. One of my favorite things to do with this lesson is to actually write this problem like on the board at the beginning of class and say how many people know how to do it. And usually nobody knows how to do it. And by the end of class, you're saying, okay, well, that was easy. And it's just a matter of knowing what the symbols mean and how to pull it apart. The trickiest part of this is actually going to be the number 54. The variables are going to be super, super straightforward. So off to the side here, I'm going to take the 54. I'm going to factor that into 9 times 6. And then the 9 factors into 3 times 3. And the 6 factors into 3 times 2. If it's a number that's so big that you don't know how to do that, you just pull out your calculator and you just pull it apart piece by piece. So if it's even, divide by 2, pull the 2 out and then see what you have left and then factor what's left. And you just have to break it down. It's a little bit tedious, but it shouldn't be too difficult. So now, remember I said these problems get really long? Just bear with me here. So the prime factorization of 54 is 3 times 3 times 3 times 2. So 3 times 3 times 3 times 2. Now the variables, super easy. X to the third is just x times x times x. And then y to the fifth is just y times y times y times y times y. When you have big exponents, do a quick count check when you're done. 1, 2, 3, 4, 5. Just make sure you didn't make a careless error. So what we've got here is a cube root, and we know that cube rooting undoes cubing. So we're going to look for these groups of cubing. Right here, I see this. This is 3 to the third power. You don't have to write 3 to the third power. Okay, don't have to write it. But if you take the cube root of 3 to the third power, you get just a 3. Right here, I see x to the third power. Well, if I take the cube root of x to the third power, I will get just x. And here I have a group of 3 y's. And if you take the cube root of something to the third power, you'll get just the y. And now that's everything. There's no more groups of 3 in there. And so we're just going to look at what do we have left. Well, I have a 2 and I have y times y. And so that's what's still left under the radical. Make sure you put the cube root there, and then y times y is y squared, and we're done. Ta-da. Okay, and that was it. That was simplifying it. We went from something big and complicated, and we got the smallest possible thing under the radical. Next example, we'll do a fourth root. So this one, I believe, does show something a little bit different. So we're going to have the fourth root of 81, x to the fourth, y to the eighth. Ouch on the y to the eighth. So we're going to do this nice big long radical, because we know we're going to have a lot of stuff multiplied out. You might need to do a little bit of work on the 81, okay? And this work you can do off to the side, or you can do it in your calculator. 81 factors into 9 times 9, and each of those 9s factors into 3 times 3. So our prime factorization there is 3 times 3 times 3 times 3. Then x times x times x times x. Now we have 8 y's. Here we go. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to do a quick check. 1, 2, 3, 4, 5, 6, 7, 8. So it stretches out long, but again, not hard. And as you do these, you'll probably start to be able to skip some of this or notice some patterns, and that's okay. That's actually normal. Now, this is a fourth root, and a fourth root undoes raising to the fourth power. So we're going to look for things that are raised to the fourth power. Well, 3 times 3 times 3 times 3 is 3 raised to the fourth power. If I take the fourth root of 3 to the fourth power, I am left with just a 3, with no more radical over it. Here I have x times x times x times x. Well, that's x to the fourth power. And the fourth root of x to the fourth power is just x. Now I have y times y times y times y. Well, that's y to the fourth power, and the fourth root of y to the fourth power is y. But this time I actually have another group of y's. And so that means I have another fourth root and nothing left over. There's actually nothing left over there. The only thing that we might do more is y is just really weird. So y times y would be y squared. And so there's your answer. Now, I have in there that we will revisit that problem. Why are we revisiting that problem? Oh, because we're going to talk about the absolute value. So there is a little absolute value hiccup in this because we're assuming the positive root and we have an element in there that we don't know is positive. So we are going to come back and revisit that problem, but not right now. All right, last example is the square root of 8 x to the third y to the sixth. How do I know that's a square root? Because I don't see an index. The implied index is a 2. So this actually works for square roots. So if you have been really bad at square roots and just perfect squares and the factoring and you just have the wrong numbers inside or outside the radical, this strategy will work for you as well. So we're going to take that 8. We do have to do a little bit of legwork on the 8. 8 is 4 times 2 and then 4 factors into 2 times 2. So when I go to write my big long radical, I am going to have 2 times 2 times 2. Then I'll have x times x times x. And then 1, 2, 3, 4, 5, 6 y's. Because it is a square root, I'm going to look for groups of 2. And I'll pull those out. So here's a group of 2. The square root of 2 squared is 2. Here's another group of 2. The square root of x squared is x. Here's another group of 2. The square root of y squared is y. Then I have another y. And then I have another y because I have those 3 groups. So I actually have 3 y's coming out. Now I still have a few things left over that I didn't circle, and those things are still under the radicals. So I have a 2 and an x still underneath. And let's clean this up a little bit. This is just weird, and you are more than welcome to just go straight to the y cubed. Okay, I get it. So this is 2xy to the third square root of 2x. One notational thing on that, make sure that your exponent on the y doesn't look like an index. So you've got to put enough space between that y there so that it doesn't look like that 3 is hovering over the index of the problem. And I have a note on that we're going to revisit that problem too. So that's pretty much the entire lesson. I'm going to put 3 practice problems up on the screen and give you a chance to work this strategy out. And then the second half of this lesson, which we'll do tomorrow, we'll talk about taking like cube roots of negatives, like what happens when you have a negative, because it's a little bit different than when you have square roots. And we're also going to revisit that idea of needing some absolute values in the answers. There's just kind of like some tricky little things that go along with this, but we don't need to do them right now. So here we go. I'll read these out loud just so you can make sure that you're reading them correctly. This is the cube root of 20 x to the fourth y to the fifth z squared. The second one is just the square root of 20. So it's bringing it back to a simpler problem that you do know how to do another way, and just make sure that we're connecting all the dots and seeing why this is the same thing. Third one is the fifth root to the fifth y to the seventh. And that should do it. For those of you watching at home, I am going to work these problems out on the next slide so that you can make sure that you see the solutions done out. Otherwise, we are done. Okay, so for that first one, we have the cube root of 20 x to the 4th, y to the 5th, z squared. And to get that 20 factored, I'm going to factor that into 4 times 5, which factors into 2 times 2, and then of course 5 is prime. So this is going to be super long. So we have the cube root of 2 times 2 times 5. Now, some of you might notice, but it's a cube root. You're looking for a group of 3, and you obviously don't have a group of 3. So you can just put the 20 back together again if you want, and just put the 20 there once you know that it doesn't have anything you want in it. We have 4 x's, we have 1, 2, 3, 4, 5 y's, and we have 2 z's, and I guess I didn't need all that space. Because it's a cube root, we're going to be looking for groups of 3. I do have a group of 3 x's right there. I have a group of 3 y's, and that's all we've got for groups of 3. So everything else is still under the radical. 2 times 2 times 5, we're just going to put that back together again. That was the 20. We have 1x, we have a y squared, and we're going to put the z squared back together again. So there's the first one. Second one was the square root of 20. Now, before I would have you recognize that you need that perfect square factor, and then we would split it up. So this is how we've been doing the simplification of square roots. But here's your alternative. We know from this page over here that it's 2 times 2 times 5. So you would do your factorization of 2 times 2 times 5. Notice that you have a group of 2. Remember, that's a square root. So the 2 comes out and the 5 stays in. It's about the same amount of work. And I just got a notification that I have a night class that starts in 10 minutes. So I don't have long. All right, last problem is the 5th root of 10 x to the 5th, y to the 7th. Now, this one is intending to see if anybody's going to try to do like 10 divided by 5 and say that's 2, like it doesn't work. Your factorization of the 10, it does factor into 2 times 5. And so here's my big long radical. So we have 2 times 5, then we have 1, 2, 3, 4, 5 x's, and 1, 2, 3, 4, 5, 6, 7. And I'm going to do a quick check on that. 1, 2, 3, 4, 5, 6, 7. Yep. And we are looking for groups of 5. I don't have a group of 5. Don't let that trip you up. No group of 5 there. But we do have a group of 5 right here. So I can pull the x out. And I do have a group of 5 y's, so I can pull the y out. And I'm left with the 2 times 5, which is 10, and down there, a y squared. So that is the third practice problem. Hopefully that went really well, and hopefully you're looking at what maybe 25 minutes ago you thought was, wow, that's a crazy hard problem. How can you do that? And now you're thinking, that's pretty easy, and I understand why.